Hello again, everyone. Welcome to our discussion of logarithmic functions and their graphs. Now, the most important thing to know about logarithmic functions is that it's the only function in mathematics that generates or produces an exponent. So if you say log of 2 equals something, or log of 1 equals, say, 0, that means that 0 or that something, some number, is an exponent of some base. Okay, that's the most important thing to remember about logarithmic functions, that they generate or produce a value, a quantity that is an exponent. Now, before we look at the details of that, as usual, I'd like to remind all of you to please take 30 minutes to 45 minutes to skim through section in the book before you watch this video or before you attend class. Then, as you watch the video or attend class, or both, during both situations, take notes about any questions you might have, or take notes on anything that you hear or see that might seem important to you. Then review all your lecture notes and go back to the book and watch the video again, and in both situations solve all the problems you see, either the ones that have been solved in the book or the ones that I solve in this video, without looking at the solutions. Preferably, even for the first time when you watch this video, you should pause the video repeatedly and solve each exercise on your own before unpausing the video and watching the solution that I present. After all that, please complete all the homework by the due date, and of course review the previous material, because all of mathematics is cumulative and we will regularly use the skills and techniques we've learned about in the past. Okay, so as I said, the most important thing to know about logarithmic functions is that they generate an exponent, and it's right at the top of this worksheet. Okay. The other thing we should know is that during the past couple of sections or couple of lessons, we talked about exponential functions. So logarithmic functions and their equivalent exponential functions are inverses of each other. We've already talked about inverse functions, right? So you know that any log function and its equivalent form in exponential form, when we say they're inverses of each other, we mean they are mirror images of each other across the y equals x line. And we will look at that in this, a couple, 2-3 examples of that in this section as well. So in combination, if you fully understand what's written in these two boxes, you will know at the very least, 70% of all things there is to know about logarithmic functions in these two boxes. First of all, that the logarithmic functions generate an exponent, and then that any log form has an exponential form. Notice that the exponential form does not have the log in it, because it's the log form written in exponential form. But these are equivalent and they are inverses of each other. Okay? Again, log functions and their equivalent exponential forms are inverses of each other. So how do we go from the log form to exponential form? Well, remembering that logarithmic functions generate an exponent, you should then look at this expression and realize that this y is an exponent. And if we have an exponent, then the question is, what is the base of that exponent? Well, the base of this exponent is the base of the log function. In this case, it would be a, the letter a, whatever that number is. So y is an exponent. A, the base of the log function, is the base of that exponent. And x is the result of a raised to exponent y. If you follow what happened here, because this list is an interpretation of the terms in this log function. If you follow that, then you have no trouble writing this log function in its equivalent exponential form. So a becomes the base, y becomes the exponent, and x becomes the result. Okay? The other thing you should know is that by mathematical convention, by that I mean an agreement between mathematicians, if that digit a is missing, that means if it's left blank, then the base of the logarithmic function is 10. So when it's 10, it's missing. Remember, let me use my scratch paper here, which I use often. Remember, with respect to the radical expressions, if the index is there, let's say 4, we have 4th root of x, right? Now remember, when it's missing, when that number is missing, we have square root, which means that number is 2. But by mathematical convention, we leave that out. Okay? We just don't write it. And if it's missing, it means it's 2. Now, with respect to log functions, if you have the log to any base, let's say base 3 of x, then that's log of x to base 3. It's there. But if it's missing, if you just have log of x, and this is missing, it's left blank, it means it is 10. Okay? So the base, if it's blank, that means the base of the log function is 10. Later on in this section, we will get to, not that so much later on, but in a couple of minutes, we will get to another notation, which is natural log. Natural log, if you have natural log of x, by definition, it means that this base is e. So if it's missing, it's missing, so that means the base is e. And you already know what e is, right? We talked about the natural exponential function in the last video. Remember that? Remember when we talked about e? So the base of the natural log function, that's the log function, and this is the natural log function. And this is just a label. ln is just a name. Natural log of x has base e, that number that we talked about. Okay? In fact, if you have log of x such that this base is e, you can write it as natural log of x. Okay? So please make sure that you follow what I've just said here. If a log function has a base other than 10, it must be written. It must show itself here. If a log function has base 10, you don't have to write it. You can simply say log of x. That means the base is 10. If you write it, it's not incorrect, but by mathematical convention, we usually don't write it when it's 10. Just like when we had square root of something, we don't write the 2, right? Because we leave it blank, so knowing that that is a square root. Also, if that log function has base e of x, then it's such an important function that it has its own form or notation in mathematics. We call it natural log of x. So if the log has base e, it is natural log of x. Okay, and it goes without saying that the natural log here has base e. Okay, I thought I mentioned that. All of that is captured here as well. So if the digit a is missing, then the base is that, 10. Right? That's what I was saying on that piece of scratch paper. The other thing that you should know is that the log of a negative number does not exist. Remember when we deal with rational expressions, these are fractions with x in the denominator or numerator. When we dealt with that, the denominator could not be 0, right? So with log functions, you cannot take the log of a negative number. Why? And we can, and as I suggest here on this paper, it says try it on your calculator. Let's do that. So here it is. I'm going to take the log of some negative number. So log of negative 5, right? This does not exist. When I press enter, it says domain error. You see that? That is a very, very important message. Why? Because this rule, the fact that log of a negative number does not exist, we're going to use that to find the domain of log expressions. Remember that. With this fact that I mentioned here, the log of a negative number does not exist, we will use that to find the domain used to find the domain of log functions. Okay, it's the same thing with respect to the natural log function, this one. Natural log function, also the same thing. Natural log of a negative number does not exist. Once again, we can look at that on the screen here. Suppose if I say natural log, notice natural log and log are such important functions in mathematics, they have their own button on a scientific calculator. So natural log of negative 8, and I press and it says domain error. Okay, so we'll use that to find the domain of a log function, this one, this rule. Below it, I have this note that says the log of a number between 0 and 1 is a negative number. Try it on your calculator. So we just said that the log of the log or natural log of a negative number does not exist, but if you take the log or natural log of a positive number between 0 and 1, you'll get a negative number. How is that? Let's see. So I'm going to say log of 0.365, right? 0.365 is a number between 0 and 1. So the log of it must be some negative number. There it is. Minus 0.4377. Okay? We can do the same example with a natural log of a number for a number, positive number that is between 0 and 1. 0.8726, right? 0.8726 is a number between 0 and 1. There you have it. Minus 0.136278 and so on. Okay? So the log of a negative number does not exist, and we will use that to determine the domain of a log function, and the log of a number between 0 and 1 is a negative number. So here, I'm just basically explaining at the bottom of this page that the natural logarithmic function is defined as that, as a log function that has base e is equal to the natural log function. And the natural log function has this exponential form, which is the inverse of that. Okay? Notice that, as usual, the natural log generates an exponent. In this case, y is the exponent. If that's the exponent, what is the base? The base is e. For natural log function, the base is e. So e to the y power equals x as the result, as you can see it here. Okay? So we get to our first example or exercise set of this worksheet. It says, given the following logarithmic forms, convert and write the equation using the exponential form. Okay? So remember what we said. That page, that one page is so important. If you understand this front page of this worksheet, you are, like I said, 70%. You can solve 70% of all logarithmic equations. Okay, and then the other 30% comes up in the next section, which is about properties of logarithmic functions. We have not yet talked about those. We will in the next section, but that's the other 30%. Okay, so they say, given these log forms, convert and write the equation in exponential form. Okay, so we already said in the front page of this worksheet that log functions generate an exponent. So that -1 is an exponent. Okay, let's write it, -1. We said that if the base is left blank, the base of the log function, that means it is 10. So the base is 10. And the result is 0.1. Okay? So then if you can look at this expression like that, if in your mind you can break it up into these pieces, then you can easily write down the equivalent exponential form of this log function or log expression. Because we say, oh, okay, so base is 10, exponent is -1, and the result is 0.1, and we're done. Okay? That is the exponential form of this log function. Before you see me write the answers for these two, please pause the video. It should not take you more than a minute to answer both of these questions. No more than 1 minute. You should be able to do it. Okay? And when you're done, then unpause the video and see my solution. All right, so I'm counting on you that you did that, and now you're back. So we know that log functions generate an exponent. So this 2/3 is an exponent. We see that the base of the log function is 8. And we can see that the result is 4. Okay, so put them together. Base is 8, exponent is 2/3, equals this result 4. Okay, that is that. I hope this agrees with the answer you wrote down on your own paper. This one, we have log that generates an exponent. So this 0 is an exponent. Exponent is equal to 0. The base is 5. Again, if it was blank, it would be 10, right? But it's not, so it's 5. And the result is equal to 1, right? So put it together in exponential form. The base is 5, the power is 0, and the result is 1. Okay. All right. So number 2, it says, given the following exponential forms, So this time we are given the exponential forms. Convert and write each equation in logarithmic form. Okay, so we already have, and again, please pause the video, answer that question, and then come back to the video. Okay, so we know that the log functions generate an exponent, right? So whatever I write on this side, it's going to have to be the exponent of this expression. What is the exponent of this expression? -4. The base is 10, so I don't have to write it. I'm going to leave it blank. And what is the result? The result is 0.0001. Like that. Okay. Again, the base is left blank because it's 10. This one, once again, make sure that you pause the video, write down your own solution, and then come back to the video after that. Okay, I'm assuming you've done that. So here, what is the exponent in this expression? -3, right? So let's put that here on this side, -3. On the left, we have to have the log function. The base this time is 2. It's not 10. So I'm going to have to write it here, 2. And then the result is 1/8. 1/8. All right? And if you convert this to the exponential form, you get 2 to -3 power equals 1/8, which is true. Okay? Next, given the following equations in natural logarithmic form, right? So now we have the natural logarithmic form. That's natural log, right? And we know natural log is simply the log to base e, right? We mentioned that. Log to base e is equal to natural log of x. Remember that? Okay, we want to convert this to exponential form. All right, so once again, I hope you've already done this on your own paper. So here we know the 5 is what? Natural log or log functions generate an exponent, so that's an exponent. Okay, what is the base then? Well, this is a natural log, so the base must be e. And what is the result? Y is the only term left. So the result is y. So let's put it together then. The base is e, the exponent is 5, and the result is y. So this is the exponential form of this natural log form. This one. We know that 4 is what? Natural log or log functions generate an exponent. So this 4 is an exponent. Okay, what is the base? The base, this is a natural log, so the base must be e. And the result is x minus 1. All right, let's put it together. So base is e, exponent is 4, and the result is, result is x minus 1. Not minus 1, x minus 1. So e to the 4th is equal to x minus 1. So this is the exponential form of this natural log form. Okay, it says, number 4, it says, given the following equation is in exponential form, convert and write each equation in natural logarithmic form. So this is the opposite of what we did in problem number 3. Okay, it's the opposite of what we did here. Okay, so we know that the exponent here is x plus 1, right? So let me put here an equality and x plus 1 on that side. And then I'm going to put a natural log notation here. And I know that this generates an exponent, so x plus 1 is the exponent. The base is e, and the result is 0.5, right there. Okay? This is the natural log form of this exponential form. This one, please make sure that you pause the video if you haven't done so and write the answer for this down before looking at my solution. Okay? It's really easy. Okay, so I'm assuming you've done that and now you're back. So the exponent here is minus 4t. Minus 4t. The base is e, so we have natural log, and the result is x. There you go. The base is e, exponent is minus 4t, the result is x. Okay. So here, number 5, it says find the domain of each of the following functions. Both of them are this one is log function, that one is natural log function, right? Remember that thing that I said we used to find domain with? That rule? The log of a negative number does not exist. And what did I write underneath it? This rule is used to find the domain of log functions. Okay? All right, we're going to use that rule. And they say write the answer using the interval notation. So we shouldn't forget to do that either. Okay. At this point, use that rule that the log of negative numbers does not exist to find the domain for these two functions. It should be easy for you to do because you're just watching this video at your convenience. And please take just a scratch paper. It's a quick process. It shouldn't take you more than 10 minutes or even 5-6 minutes to answer both questions. But please don't proceed with this video unless you've given yourself the opportunity to write down the answer for this first. Okay? It doesn't matter if you don't think you can answer this. Try it. The rule you're following is that the log of a negative number does not exist. Okay? Just use that. Okay, I'm assuming you've done that, and now you're back to compare your solution with mine. Okay, so we know that the log of a negative number does not exist, right? So let's use this to our advantage to find the domain of this log function. So that means 8 minus 2x must be greater than 0. One thing I forgot to mention is that the log of 0 also does not exist. So if I bring back my calculator here to just demonstrate this, so the log of a negative number does not exist, yes, but also the log of 0 does not exist. And the same is true for the natural log. So log of 0, domain error. You see that? And let me do the same thing with natural log. Oops. Natural log of 0. Again, it's domain error. So that means this argument, the argument 8 minus 2x, is called the argument of this function. 8 minus 2x must be something positive. It cannot be 0. It cannot be less than 0. It must be always greater than 0. So we set up this inequality and then solve for x. So we have 8 greater than 2x, right? We move the negative 2x to the other side. It was negative on this side. On the other side of the inequality, it becomes positive. Then we need to isolate x. So what do? The 2 is preventing us from isolating x. So we need to get rid of this 2. So divide both sides by 2. And what do we get? We get 4 greater than x. In other words, or x less than 4, right? This or that makes no difference. So they asked us to write the answer using the interval notation. So let's do that. We will write anything less than 4, right? So negative infinity, comma 4, bracket or parenthesis. Which one would you use, bracket or parenthesis? Parenthesis, right? Because 4 is not included. There's no equality under this. 4 is not part of the solution. Okay. Now here, I hope this agrees with your own solution. On this side, the same thing. A natural log of a negative number or a natural log of 0 does not exist. So this term, this x minus x squared must be greater than 0. Something positive, something non-zero and positive. And that's the condition. That's inequality satisfies that condition after we solve this inequality for x. Okay, so let's factor this. This is a quadratic inequality. Remember how we solve quadratic inequalities? Remember that? We need to find the boundary solutions and we need to test a number in each region of the real number line. Remember that? That's why I keep asking you guys to please spend 30 minutes a week to review previous material, because all of this is connected to each other. So factor this, we get 1 minus 1 minus x greater than 0, right? We get that. Now x equals 0, and then 1 minus x equals 0, so x equals 1. So we have two numbers that are boundary solutions. These are our boundary solutions. Remember, if you've been reviewing like I've been asking you to, that one, you know what I mean when I say boundary solutions. We know that the argument here, x minus x squared, is going to be 0 at these two numbers, at x equals 1 and x equals 0. Okay, so let's set up our real number line. So 0 and 1, we need to have a hollow circle there and a dashed line. So 0 and 1 cannot be part of the solution. But this is a quadratic inequality. We did talk about a few lessons ago. We had a video on this, right? We talked about that we have to find the boundary solutions and then test each region. Remember that? Okay. So now let's test a number in this region, a number in this region, and a number in this region. Knowing that 0 and 1 themselves, the boundary solutions themselves, are not part of the final solution. So I'm going to test the number in this region. So test x equals -1. Okay. I'm going to plug that in this inequality. Okay. -1 minus -1 squared. We ask, is that side, we're testing that. That's what we're testing. Okay, right here. We're testing to see if the left is greater than 0. So let's see. Minus 1. That minus 1 squared is 1. Positive 1 is minus 1. And we get minus 2 greater than 0. Is that statement true? Is negative 2 greater than 0? No. No. So that's this region, no, is not a solution. Okay. So let's test the number in the middle. Let's say 0.5. We tested x equals negative 1 and it didn't work out. So test x equals 0.5. We're going to plug into that inequality again. So 0.5 minus 0.5 squared greater than 0. We're checking that. So this is 0.5 minus 0.5 squared is 0.25. And then 0.5 minus 0.25 is positive 0.25 greater than 0. Is this a correct statement or result? Yes. 0.25 is greater than 0. So yes, this region is acceptable solution for that natural log function. Let's test the number in this region. So let's say 2. Test x equals 2. We're going to plug into this inequality, right, to see if the inequality is valid or not. So 2 minus 2 squared greater than 0. We're testing this. So 2 minus 2 squared is 4. We end up minus 2. 2 minus 4 is minus 2 greater than 0. Is that a valid result? No. Minus 2 is not greater than 0. So no. Okay. So looking at this, and we did this, why? Because we have quadratic inequality that must be greater than 0, right? That's why I'm asking you guys to review previous material. So looking at that, the solution is between 0 and 1. So 0, 1 is the domain of that expression. So this is the domain. Sorry, I've encroached down into this, but it's okay. We should be okay. So this is domain, and that is the domain of that expression. Okay? All right. So next, it says find each of the following without the use of a calculator. Okay? So we know that the base is, so we're evaluating this. What is the log of 9 to base 3? Okay? So the result is 3 squared. Right? So this is some exponent. In other words, this is asking us what exponent should be here. That exponent would be to base 3, right? So they're asking 3 to what exponent is equal to 9? Can you do this without a calculator? Absolutely you can. Right? That means that that result, or I should give it that, is equal to 2. So log of 9 to base 3 is 2. The same thing is here. They're asking us to evaluate this. That means they're asking for us the exponent. To what base? To base 2. They're asking 2 to what exponent is equal to 64. Well, 2 to the 5th power, 2 squared is 4. 2 cubed is 8. 2 to the 4th power is 16. 2 to the 5th power is 32. 2 to the 6th power is 64. So the answer to that is 6. Right? They're asking for the exponent of base 2 that would give us 64, just like what I've shown here. Okay? Okay, so go ahead and answer the rest of this. All of these, there are 5 examples that are remaining on this page. Answer them. So pause the video, answer those 5 blank ones, and then come back to the video and see if you have the same answer I get. Okay? I'm assuming you've done that and now you're back. Fantastic. So here, once again, they're asking log of square root of 10, evaluate that. So they're asking for the exponent. To what base? To base 10. Right? They're asking to what? That question is that. Question mark is that. The base is 10 because it's missing, remember? So 10, the base 10 to that question mark equals this result. They're asking what that exponent should be. Well, long time ago, we learned that any radical expression can be written in terms of a rational exponent. So let's do that. So 10 to question mark is equal to 10 to 1/2 power. Rational exponent, right? This is the same thing as that. So compare the left and right. Do you see what that question mark should be? The bases are 10. The only way the two sides can be equal to each other if this question mark is going to be 1/2. So the answer there has to be 1/2. We figured out that exponent. Okay. And this one says figure out the exponent such that it is equal to this term. Well, 3, this 3, not that. This 3 in the base to that exponent must be equal to this result, 3 to -2 power. And let me move this up. So once again, the 3 you see on this side is the base here, not that big 3, this little one, the base 3. To that, this base 3 to that power, which we're looking for, must be equal to this result, 3 to -2 result. Compare the left and right. The only way the two sides can be equal is that if that question mark is equal to -2. So -2 is the result of that. Right? We've been able to do this without the use of a calculator. Okay, the last two. Or this one also, sorry. So we have that one too. We have these 3. We have these 3 still left to do. This one, and this one. Okay. Okay, so here we have the base, which is 2. And so they're looking for an exponent, right? Evaluating this log function means that we're looking for an exponent. So, exponent to what base? To this base 2. So 2 to that question mark, which is the exponent, power, equals this result, which is square root of 2. Okay? We know we can write any radical expression in terms of its rational exponent. So let's do that. 2 to 1/2 power. Okay, compare the left and right. The only way the two sides can be equal to each other if the question mark is equal to 1/2. So therefore, the result here, which is that, it's going to be 1/2. Okay. 1/2. Okay, here. So once again, we're looking for this, evaluate this. That means we're looking for an exponent. To what base? To base E. That's not that E. That E that you see is part of the result. The base E is not written, but we know it is there because this is a natural log function. So natural log, this is the E that is missing, that base, to this question mark must be equal to this result, e to negative 5 power. Okay? So this e, once again, to the question mark, is the one that is missing, because by mathematical convention we don't write it, but it's there. I mean, it's not missing, it's there, but by mathematical convention we're not writing it. It's right there. So that e to this question mark as power must be equal to e to negative 5 power. Okay? So then we have the question mark. So compare the two sides. The only way these two sides can be equal to each other is if the powers are equal. So the question mark then must be equal to negative 5. Like that. Okay? Do these answers agree with yours? If they do, wonderful. That means you're making wonderful progress here. If not, please make sure that you get answers to your questions. Okay? So here, again, it's a log of 4 to base 64, and they're asking us to evaluate that. So that question mark is an exponent, because we know natural log and log functions generate an exponent. So exponent to what base? To this base. So 64 to some power must be equal to 4. Okay? Well, can we write 64 as powers of base 4? We can. So this would be 4 to third power is 64, right? So 4 to base to power 4 at 4 cubed is 64, and that equals 4. So 64 to some power must be equal to 4. So this is, then that means if 4 cubed is 64, then cube root of 64 is, cube root of 64 would be equal to 4. So that would mean that we would have to, okay, so this would be 2 squared, or 2 to the 6th. It would be easier if I just wrote it here. Because 4 cubed is 64, then cube root of 64 is 4. So that would be 64 to what exponent is 4? It would be 1/3. So let me revise this, because, well, let me write it here. So I'm going to add something here. We know that 4 cubed is 64. Okay? Therefore, cube root of 64 is 4. So cube root of 4 cubed is, cube root of 64 is equal to 4. Cube root of 64 is equal to that, 4. So the answer here would have been 1/3. So 1/3 here, like that. So 1, let's see. So 64 to 1/3 power, this question mark should be 1/3. Okay, so this is the same thing. I mean, this is not necessary, actually. Knowing that, we can say that this question mark should be 1/3. So the evaluation of this would be 1/3. Okay? So this should be, this is 64 cubed is 64, and then 1/3. So that question mark should be, like that. So either you're dealing with this or that, because if the question is 1/3, if the question mark is 1/3, what do you get? I mean, this was not necessary. If you remember this, this is not necessary, but it's fine. So if you have 4 cubed to 1/3 power, which is what we have, right? 1/3 times 3, 1/3 times 3 is 1, right? So we end up with 4 equals 4, which is that. Okay? But all you need to remember is that, and then you'll get to that answer. But this is another way of getting that answer. Either this or that will lead to that answer. Okay? Which is not using the calculator. That's all they're saying. Okay, so here they're saying graph the function and its inverse, right? This is the log function. This is its equivalent in exponential form. So graph the function and its inverse on the same set of axes. Use any method, manual selection of points on the graph or a graphing calculator. Okay, I'm going to draw this. You should have, I mean, we will rarely, maybe in one occasion on an exam somewhere, but very rarely draw the graph of a log or natural log function by hand. Okay, it's a tedious calculation by hand, so we're not going to do it. But the point of this last two exercises that I have, one you see on the screen and the one right underneath it, we'll get to that in a minute, is that you should be, not that you draw these graphs, but you should be familiar with how the graphs of log functions and exponential functions look. That you must be familiar with. So you must be able to look at a graph and decide, is it linear? Is it exponential? Is it logarithmic? That's what we are aiming for in this course. Okay, not that you draw it, but with your eyes you should be able to recognize what pattern of function a graph has. Is it linear? Is it quadratic? Is it exponential? Is it logarithmic? That's what the goal is here. Okay, so the log function, first of all, this is an easier function to draw because this is this base is greater than 1, and as you recall when we talked about exponential functions, any base that is greater than 1 is an increasing exponential function. Okay, and if that base is between 0 and 1, then it's a decaying exponential function. Do you remember when we talked about that? So we know this is an increasing function, so it goes like that. But the y-intercept would be wherever the x is 0, right? So if you plug in for x with 0, you get 4 to 0 power, you get 1. So let's say that is 1. Let's say that point is 0, 1, right? I could have put it here, but I want to make it more visible here, 0, 1. So the graph of this function, it's an increasing function, and it's going to go through that point as the y-intercept. So it's going to go like this. It's going to go look something like that. Like that. Okay? This is f inverse of x like that. And I graph this because it's easier. Now that one is the inverse of that. So do you remember what we do with the inverse functions? They are the image of this function across the y equals x line. Remember that when we looked at the functions and their graphs? So let me draw this dashed line, oops, I'm not using my ruler here, but let me try to make this as straight as possible, like that. So that red line is the mirror, y equals x. So then the log function, which log of x to base 4 function, which is the inverse of that, would be the image of that across this mirror line, which is y equals x. So it would be, we know that the log of x does not exist, right? Let me write that here. Log of not x, that doesn't, log of 0 does not exist. Log 0 does not exist. That means at x equals 0, which is the the y-axis. The y-axis is has equation x equals 0, right? On the y-axis, the x values are 0 for any point on this line. Okay? So because the log cannot exist on this line, that means we cannot intersect this line. Okay? And we know that log of 1 is 0. So log of 1 does exist and is 0. So that is 1, 0. So the line for this function is going to go like that. It's an increasing function, but it's going to go like this. Like that. Okay? But these two lines should be mirror image of each other. And I didn't do too bad of a job drawing them as such, that they look like the mirror images of each other. But after we're done with this, we're going to go to the computer and we're going to look at them on the computer. So this one, though, I should have drawn it with another ink, with another color, but I forgot. So let me write down that this function is f of x equals log to base 4 of x. Okay? And that one, that is that. This function is that. Okay? All right. So that's what we care about, that you are able to recognize these graphs, this one as a log graph, and that one as an exponential graph. That's what we care about. Okay, so this one, we want to, again, this is the most famous natural exponential function. This is the most famous functions of that. And this is the natural log function, right? They are the inverses of each other. Let me draw this because it's easier. So we know that when x is 0, f of x is 1, right? So that would be that, 0, 1, right? When x is 0, the function is 1. So this line, once again, it's going to go like this, like that, and like that, okay? And I should actually put arrows on all of those lines that I drew there on the previous example. So, but this is an increasing function, right? Read it from left to right. It's increasing. Then the natural log function would be the inverse of this. So once again, it would be the mirror image. This would be the mirror image of this across the y equals x line. And I will try as best as I can to draw that mirror, which is the dashed line, like that. So that dashed line is the mirror, y equals x, right? All points that have equal x and y coordinates are on this line. 9, 9, 10, 10, 100, 100, all of that. 2, 2, they're all on this line. -5, -5, -10, -10. That's the mirror. Now, how would the natural log of x plot? Well, we know that natural log of 1 is equal to 0, right? We can, I mean, these are some, the more you work with these functions, the more you find out about them. So natural log of 1 is 0, right? We know that. So that means when x is 1, the function value, the inverse function value is 0, right? Which is that point. On the other hand, we know that the natural log of 0 and negative numbers do not exist. So x cannot be 0 or negative. So this side is out of the question. So the line for this function, the graph of this function, must start from this side, above 0. It cannot be 0. As we said before, if you're on the y-axis, the x value or the x coordinates are 0. For all these points on the y-axis, x equals 0. So the line graph for this function cannot be on this line or cannot cross it. So it's going to come like this. Then it's going to go through that point, and it's going to go like this, increasing. It's not going to curve back down, but it's curving like that, and it's increasing. Okay? So this is f natural log of x, and this one is f of x equals e to the x. Okay, they're inverses of each other. Okay, so we're almost done with this section, but I promised you that I would go to the computer and graph these on the computer before we wrap up this section. So as I switch to the computer, please remember that your screen is going to blank out for a second, but don't mind that. It's just that me transitioning from dock camera to the computer. That's all. So let me do that now. Okay, we're back. So we want to graph y equals log of x divided by log of 4. So this is the way we can graph this function, because this computer does not have log to base 4. So I have to graph it like that. And then g would be equal to 4 to x power. And let me graph also the y equals x line right there. So the green line is the mirror, which is y equals x. The blue one is the y equals 4 to x power. And the red one is log of x to base 4. You can see that both functions, the log function and the exponential functions, are increasing functions, but the exponential function is a more rapidly increasing exponential function. Log function is an increasing one too, the red curve, but it's increasing at a much lesser rate than the exponential function. Okay, but you can see how they're inverses of each other. So let's graph the last two, which were y equals e to the x. That's the exponential function. And then also g is equal to natural log of x. There. And let me also write there. So this is the graph of the natural log of x and e to the x functions. As you can see, they're inverses of each other, right? They are mirror images of each other across the y equals x line. With that, we have come to the conclusion of another lesson. I hope this was useful, and thank you for persisting through this video with me. For now, have a nice day, and I will see you all again next time.